Okay, everyone, let's get started. So today we're going to have a lecture primarily on the iPad. I had a couple slides, so our topic for the day is BERT. Actually, before I get to the iPad, I just wanted to note that a lot of you asked for the due date of the final report so you could plan travel and stuff. The report will be due May 12th, which is the last day of final exams. This means that your final report, the PDF, should be submitted to Gradescope, and your code should be submitted to the instructor's email account. We have not decided as of yet whether we will have presentations as well, but if we do, they certainly will not be in class or live or anything. They might require you to upload a video, like a short video describing your project. But we still have not decided. In previous semesters, there has been no presentation component, and students would like to see other students' projects, so there might be one this semester, but definitely no live thing. You do not have to be here to submit your final report, and yeah, hopefully that is helpful for you to plan. Okay, so any questions on logistics or proposal-related stuff? Your proposals are due this Friday, so please be working on those. Yeah. What's that? Oh, homework 0, the grades have been completed. I think the graders are waiting to cross-check before publishing the grades. They should be available either today or tomorrow. Also, homework 1 will go out next week since we extended the project proposal deadline. So we'll give you a few weeks to do that as well. All right, so let us switch over to the iPad. Oh, my bad. So the YouTube people did not get to see this, so this is what I was sharing on my screen. Basically, the final project report is due May 12th. It'll also be put up on the course website in case you missed it here. All right, so let's go back here. Okay, so last time, if you remember, we left off by starting to describe transfer learning with language models. So we started describing ELMO, which used recurrent neural language models to pre-train and then solve some downstream tasks. Today, we will basically go from ELMO to BERT. And BERT kind of forms the foundation behind many of the subsequent transfer learning, transfer learning methods that we will talk about for the rest of this semester. All right. So I wanted to start by continuing where we left off with the ELMO approach. I wanted to fully specify it and then point out some limitations which kind of will segue into our description of the BERT model. Whoops, what did I do? Go away. Okay. So if you remember, our goal was given some sentence like this movie, whoops, is good. We would have some kind of model that would create a vector representation of this sentence, and then we could pass it into a classifier. So the traditional approach, which we talked about in the last class, was that we would have some sort of recurrent network or some sort of feed-forward network trained over this sentence and other labeled sentiment examples, and on top of the final hidden state of the sentence, we would add a softmax layer to predict positive. And everything trained from scratch. So this was, again, the pre-2018-ish approach. And we talked about some of the limitations of this, where you have a neural network that's trained from scratch on labeled sentiment data. Can someone tell me what are some limitations of this approach? So the data may not be available, meaning, well, if I can extrapolate, you will always have a limited set of labeled data for this task, right? So how many reviews with scores can you collect? Maybe millions or tens of millions off the internet, but you have so much more unlabeled text, right? You could crawl the entire internet, and your model is not able to leverage the knowledge that is in the unlabeled text to solve this problem. So that was the main issue with this kind of setup, which motivated using transfer learning from a much bigger model trained on much more data. So in Elmo, we basically proceeded in 2 steps. So step 1 was pre-train an RNN language model on lots of data, lots of unlabeled data. And we will go over these terms pre-train, fine-tune, frozen a little later in this lecture after I've introduced all of them. Here you can just think about we are training from scratch a giant language model on a lot of data. So this is step 1. And we've already seen how to do this, right? So given this movie is good, we have embeddings for each one. We have an RNN that computes these hidden states using the RNN update equation. And this is a language model, so at every time step, we're going to predict the next word. So this movie is good, end of sequence, or something like this, right? So I have as many sentences as I can get from wherever, the internet or Wikipedia, and I can pre-train this RNN language model on this task of predicting the next word, right? So for Elmo, we pre-trained this thing, pre-trained on about 1 billion words. So, like, it's fairly large for that time. Of course, now we have models trained on hundreds of billions of words, but for 2018, this was pretty large given the computational budgets of our resources. So we got this RNN language model, right? And all of you should understand how this is trained, what the task is, what the training objective is, how you do the parameter updates, and so on. We talked about all of this throughout this semester. So given this RNN language model, the next step is to freeze the LM parameters. So again, I'll highlight some terms that we will talk about in detail later. So first is pre-train, second is freeze the LM parameters, and use its representations. By representations here, I mean the hidden states as input to a task-specific model. So let's say I have this model. Let me copy it from over here. This is my language model. Put it down here. There's these. So I'm very interested in extracting these hidden states over here because they contain a lot of knowledge about the words in this sentence, right? We already know that in order to predict good, given this movie is, the model has had to learn a lot of linguistic information and world knowledge and the fact that movies can be good or bad and things like that, right? So this is very useful information for a downstream sentiment classifier. So if I'm able to extract all of these states, then I can, so maybe I'll write that. These are the hidden states from LM. Then I can put these hidden states into a sentiment model. So we can call this a sentiment NN. So this could be any composition function that takes, you know, a sequence of vectors and outputs a single vector. So we've seen several things that could take the part of this. An RNN, for instance, you could put all these through an RNN and take the final hidden state. You could add these 4 vectors together. You could average them using these element-wise functions. You could pass them through a concatenation and feed-forward layer. You could do lots of different things, right? But the important thing is that the input to this neural network comes from this big pre-trained language model. And, sorry, let me move all of this down. So after I feed these hidden states into my sentiment neural network, I will apply a softmax layer to predict positive. So in this setup, I have the neural network language model. How do I change my brush stroke thing? Okay, I forget how to do that. Maybe I can use a different color. So this part of the network here, this is frozen, meaning when we apply backpropagation to train the sentiment neural network, I do not backpropagate into the language model. That's because the language model we're treating as kind of a feature extractor. So it has some knowledge about language, we trust its knowledge, and we don't want to corrupt it by the sentiment signal. So instead we have this sentiment neural network that's over here. And these parameters are all trained from scratch. So it receives the input in the form of the language model's hidden states, and it uses those inputs to produce a sentiment label. So the two models, the pre-trained language model and the sentiment network, are connected, but backprop, so if I'm going to do backprop here, like I will go down this, I'll go over here, the gradient flow, that's what I'm drawing with these backward arrows, but then it stops. There's no more gradient flow into the bottom part, the language model. It's been pre-trained and then frozen. The parameters do not change based on the sentiment network. So this has some advantages and disadvantages. The advantage is that this language model on the bottom can be very big and it can be very deep, and it can also be very expensive to do backprop into all of the language model's parameters. So by keeping it frozen, I can actually cache the outputs of this language model and not even include it as part of my sentiment neural network computations. Like I can just run the forward pass once, get all of the hidden states I need, and then use those as inputs to my sentiment neural network. The downside is that by not fine-tuning this model, the language model doesn't actually know that it's being used to solve a sentiment analysis task. So you could imagine its parameters could be further specialized to extract things like emotions or sentiment containing words, or do better at negations and things like that if it were fine-tuned with the sentiment signal. So its hidden states could have more of that information. So there's kind of a trade-off between computational efficiency and performance here. Also, if you have very few labeled examples, it's probably bad to fine-tune your base language model, at least with a high learning rate, because you don't want noisy signal corrupting all of the stuff that it's already learned during the pre-training stage. Okay, so any questions about this setup? Basically, there are two steps. You pre-train a language model, then you add a new task-specific network on top of the language model to solve whatever task you want. Here, it was sentiment analysis. So the question is, does this always work? Meaning, is this always better than just doing this, perhaps, and having no language model? Is that your question? So in this Elmo paper, our experiments were primarily on English tasks. They were all on English tasks. And for 5 or 6 completely different unrelated tasks, so like sentiment, question answering, parsing, other things, there was all a significant improvement by adding these language model representations. And subsequent work has shown that this is also very effective in different languages as well. And we'll talk more about these multilingual language models and using them for transfer learning later on in the semester. So yeah, it's generally always good to do this. In fact, the language model pre-training step can be useful even when your downstream task doesn't involve text at all. So people have shown that you can use a pre-trained language model to help you learn to solve Atari games, or like learn agents to play Atari games, which is kind of crazy. That was a recent paper. But like, it seems like this knowledge, whatever this thing is learning, is generally kind of applicable to many different things. Yeah.
What happens, let's say that the pre-trained model is trained on before data, whereas your application is the healthcare application.
Yeah, so the question is, what happens if your pre-trained language model is trained on a different domain than that of your target application? So we will talk about some ways to get around this kind of issue, which kind of involve intermediate training of the language model on domain-specific data. Like, you can further train your language model on the text without the labels in your domain. But in general, the pre-training phase, people generally conduct it to have as much diversity in the data as possible, so have as many domains and even nowadays languages, styles as possible, so that it'll be, you know, applicable, or at least a decent starting point for most tasks. Obviously, this is not possible for every domain, but yeah, the pre-training phase is meant to be performed one time and then reused over and over for multiple different tasks that people care about. Okay, so let's actually dig into some of the details, which will motivate our discussion of BERT a little bit later. Oh, I should also check the YouTube questions. Okay, there are no YouTube questions. Good. All right, so in the way I've just described it, we have trained an RNN language model, right? One of the issues with an RNN language model is that every hidden state only has information from the current word and all of the words that preceded that word. In reality, though, if I'm doing a sentiment analysis task as the task that I care about, I don't really need this constraint, right? I might want the word movie to know about the word good later on, because that would be good for solving a sentiment analysis task, right? In general, I might want every word to be contextualized with every other word in the sentence. So we've seen one way to do this with the architectures that we've discussed to this point, which would be have a transformer encoder and just use unmasked self-attention, right? So in this case, every word's representation is a function of every other word in the sentence, right? Every single word in the sentence. But this paper was kind of done around the same time as a transformer was released, and so we had just RNNs right? And in an RNN, you go left to right, so every representation by design doesn't have any information about the future, which is good for a language model, probably not so good for a text classification task. So in Elmo, we basically just had two language models, a forward language model and a backward language model. And these were concatenated together, their hidden states, to provide a contextualized representation. So what does this mean? Maybe I can actually even paste this again. So this was my language model in the forward direction. So here I predicted movie, here I predicted is, here I predicted good, here I predicted the end of sequence token. But now I can have, so this is the forward LM, and let's color its hidden states using this. So this is one component of the model. The second component is a backwards LM, which looks similar. It has the same architecture. However, the inputs are reversed. So my inputs here would be something like good is movie this, and my predictions would be to predict movie this beginning of sequence. So I have a forward LM, I have a backward LM, and maybe we can highlight this one with different color. Let's see. Oops. So given a sentence, I run the forward language model on a sentence, I reverse the words in the sentence and run the backwards language model. So note that now if I combine some of these hidden states together, I can have a representation of the entire sentence, right? So for example, this hidden state here, this one, has access to this movie is, but it does not have access to the word good because that comes in the next time step. Now, this time step over here has access to good is, but not the rest of it, this movie part. So if I combine these two hidden states, I have a single, if I concatenate them, I now have access to all of the words in the sentence. And then my neural network, the sentiment neural network on top, can learn to leverage this information in some way. So that's a general idea, but you might be thinking this is, kind of hacky. Each of the pieces of this language model, the forward and backward language model, they don't individually have access to the full context. It's only after the concatenation that they work. So combine via concatenation. So in the end, I have states like this movie is good. The hidden states look something like they're kind of, half of them are from the backward part and the other half are from the forward part. So these are the concatenated factors. So this is eventually the final output that is sent to the sentiment neural network. And in Elmo, there were many layers of this forward and backward language model. So I've just shown one layer RNN, but you can stack as many of those as you want. So we stacked, I think, 2 or 3 of these layers and then took the final layer representations, kind of combined them with all layers, representations using a linear combination, which is not relevant really for this class, but you can read more about it in the paper that was assigned as reading. Did you have a question?
Unmasked self-attention will also make something which is better and why are we different over it?
So I'm just teaching you this to kind of segue into the transformer version of this model. This is not the way you would want to do this now because, as you say, this requires training two separate models, each of which is, you know, independently not knowing about the rest of the context. Unmasked self-attention, you just have a single model and you can easily contextualize it. You just need a good training objective, which is what we'll talk about next. Like, how can you use a transformer to accomplish the same thing? Yeah.
Do we do this at each layer or only at the
Yeah, so the question is, do we do this at each layer or only at the top? This happens at each layer. Yeah.
you know, achieve the same using a single bi-directional
So the question is, this is a good one related to your question. Can we not achieve the same effect using just a bidirectional RNN? The answer is no, because look at our training objective. Our training objective is to predict the next word given the input representation. If we use a bidirectional RNN, the representation already has information about the future words and the previous words, so our objective is trivial, right? That's why we need to have two separate models to prevent the information leakage or the cheating at pre-training time with the language modeling objective.
but aren't we combining the identities from both the language models?
Yeah.
So is that like the advantage from both the sides?
Yeah, we are concatenating the hidden states from the forward RNN and the backward RNN, but each of those is trained separately from the other to avoid the information leakage problem.
So is the RNN going backwards, trying to predict, like, given all the future words, does it try to predict like the first word?
Yeah, so you can see what's happening here. The backward LM, it gets as input the sentence in reversed order. So given good is, it's trying to predict the word that comes next in the reverse sequence. So it's going backwards. I mean, this is a very unnatural task, right? For a human, it would be hard because we don't read reverse sentences. It's basically a hack so that when you combine the forward and backward hidden states, your representation sees the entire context. But we can do better, which is what we're going to talk about next. You all should understand, I mean, we haven't talked about bidirectional RNNs in this class, but you should go and understand why you can't actually train a bidirectional language model. It has to do with cheating and trying to predict something that you've already seen in your representation. Yeah.
So why does the backward LM help there?
So why does the backward LM help? The reason is, if you only use the forward LM, each of these hidden states here has only seen a prefix of the sentence. It has not seen all of the words in the sentence, right? Because the RNN is proceeding left to right. That's important for language modeling when we cannot allow any information from the future to go into the current hidden state. It's not important for sentiment analysis, which is maybe one task that we want to solve using this method, right? Because in sentiment analysis, our goal is to predict a label given the whole sentence. So we don't really care that, you know, this representation shouldn't have any information from the rest of the sentence. That's why it might actually be in our advantage for every one of these hidden states to have information about all of the other words in the sentence. This is not something you should do nowadays because we have transformer encoders, but it's instructive to see how that we kind of evolved from recurrent neural networks being the dominant model in NLP to something like transformers where this isn't an issue. Yeah. So the question is, if you were to use this method, I assume you mean this like pre-train and then add another module on top, what would it be best suited for? In general, it's suited for any NLP task. So the concept of pre-training a language model is almost always going to be helpful to solve any sort of NLP task. Yeah, so there's no one specific answer. Many papers have shown that this is effective for basically every task.
Are there other ways to combine both concatenation?
Yeah, so the question is, are there other ways you could combine both of these representations? You could certainly do many things. You could add them, you could average them, you could put a little network on top of the concatenation. It really doesn't seem to matter too much what you do. But again, like all these details are not super important. The important thing is that in this particular approach, you have to train two separate language models, which is a little clumsy, and we can do better. So let's move on here. So the forward and backward LM is clumsy, especially since the backward LM is like just literally a hack so that you can get full context. No one cares about this task. Can we replace these with a single model? So you might, as many of you have even brought up, why can't we just use an unmasked transformer as an encoder? The problem is, again, with the pre-training objective, right? If I'm doing next word prediction, then I always need all the future words to be masked. So we actually need to come up with a new pre-training objective to allow us to take advantage of our unmasked transformer encoder. So this is what happened in the transition from Elmo, which was 2018, to BERT, which came out the next year. So the changes were, we went from 2 unidirectional LMs, which were the forward and backward ones in Elmo, to 1 masked language model. So this is an important concept that we will focus on for the rest of this lecture. A couple other things changed. We went from recurrent neural networks to transformers. We went from fine-tuning, I should write this the reverse way. We went from freezing the LM to fine-tuning it. So we'll talk about what that means in a bit. And finally, the last step was more engineering related. We pre-trained the LM on way more data with a way bigger model. So these were the primary changes that were made, and they all in combination were very effective. So let's start with the masked language model, which is probably the most important change that was made because it allows us to use a single encoder instead of 2 encoders. So remember that we talked about language modeling as a task of predicting the next word. Masked language modeling is different in that you receive an input which is a sequence where some tokens have been randomly masked out. And your goal is to predict the identity of the masked tokens. So this is slightly different than the language modeling approach, which is given a prefix, predict the next word. Here I'm giving the complete sentence, but some of the words are randomly replaced with a masked token, and only at those positions in the sequence am I going to predict the identity of the missing token. So let me draw this out and then I'll take a question. So remember our example from before, which was students opened their books and students opened there and we were trying to predict books. Here we will use that same example to illustrate masked language modeling. So we have students, but let's say the word opened was actually masked. So we have a special mask token. So this is an entry in our vocabulary, this mask token. It's only to be used when we've eliminated a word from the input sequence and replaced it with this mask, and we want to predict what goes into this mask token. So like predict the missing word is essentially the task here. So we have students mask their books. And hang on, let me move this down. So now we're going to feed this input sequence into a transformer encoder. So we've seen these before. I'm not going to go through any of the computations. If you are not remembering like what's going on here, you should look back at the previous lectures when we talked about this. Unmasked transformer block xn, right? We can stack as many of these things as we want, and the input is this. So of course we do the same thing. We add the position embeddings to these word embeddings, pass it through a lot of these unmasked self-attention transformer blocks with the residual connections and whatnot. And then in the end, we have our final layer token level representations of this sentence. Right? So now, in language modeling, we would use each of these representations to predict the next word. Here, of course, we cannot do that, right? Because we used unmasked self-attention. So this representation student is aware of all of the different words that come in the future. So we can't predict the next word. So what we can do is, for the token that corresponds to the mask token, the one right here, we can put a softmax layer on top of this particular position to predict the identity of the missing token. So here, to predict the word open, which is the ground truth word, right? So if I'm using masked language modeling, I can actually take advantage of the unmasked self-attention here because I'm not actually leaking any information about what I'm predicting, right? Why am I not leaking any information about opened in this unmasked transformer encoder? Exactly. So the word opened doesn't even appear in the input, right? It's been replaced with a mask token, so the model can attend over whatever it wants. It just doesn't have the representation of the missing word anywhere. So this is a valid objective function. Now note that this formulation doesn't allow you just naively to predict the probability of a sentence like a standard language model would. This masked language modeling was at least developed initially solely as a pre-training task. So no one actually cares about the masked language modeling task. People care about using the pre-trained model to solve other tasks via what we will now go into as fine-tuning. So another thing you might be wondering is, why is this pre-training objective? Why does this force the model to learn useful linguistic properties of the input sentence? So the motivations for this task are very similar to those of language modeling, right? In order for the model to predict the word opened, it needs to understand, first of all, that it's likely that a verb comes in this mask slot. It's likely that students or books are things that can be opened, right? There's some world knowledge. Students are people who read a lot of books, maybe not nowadays, but certainly that's a population that interacts with books more than other populations. So it learns lots of things, just as a language model would. except in this case, it's learning from both sides of the mask token, right? So the preceding context and the subsequent context is used to come up with this representation that eventually we apply the softmax layer over. So any questions about this? Yes?
Suppose if we have more than one mask token and we want to predict say 10 words inside a paragraph,
Yeah.
does it matter how we initialize the mask token with the embedding?
So the question is, suppose we have more than one mask token in a given sequence. And usually when you're doing this kind of training, you have more than one mask token. So in the original BERT paper, they masked 15% of all tokens in the input. So I guess your question was, do you represent those different mask tokens differently? No, you use the same mask embedding for all of them, but remember that you're also using position embedding. So you will know that this mask token occurred at this position compared to this other mask token. So that's how the model can differentiate them. But that brings up an interesting point, right? If I have multiple mask tokens in my input, the task starts becoming harder and harder. So you can see this, maybe I can just use this example to illustrate that. So let's say we can call this effect of increasing mask percentage. So I can have this sequence, students mask their books, in which only one of the input tokens is masked. And so in this case, I have complete knowledge of all of the other words in the context, right? So this is like the best case scenario. The model has as much information as it possibly can to predict what goes into this mask. On the other hand, imagine if I took this sentence and I replaced this token with a mask. Suddenly it becomes much harder to predict both of these mask tokens, right? Because now I don't really have any knowledge of what was being opened, or if I'm predicting this final mask, I don't even know what verb was applied to this. So the model will find it extremely hard to make a reasonable prediction for both of these slots. So, you know, I could do this further, right? I could mask out students also, and now the model has no idea what to do, right? So there's a balance between masking out, you know, as few tokens as possible to give the model as much context as it can to predict the missing words. But on the other hand, if I only mask one token in every input sequence, I only get one prediction for that whole sequence. Versus in language modeling, I get a prediction at every time step. So I get way more signal that is backpropagating into my parameters and adjusting them. Here, for every input sequence, I just get a single error signal, which is backpropped into the parameters. So I might have to see way more inputs in order to train this model. So in the original BERT paper, they settle on mask percentage of 15%. So that means 15% of the tokens were masked. They found that this was the best balance between training efficiency and performance. I think last week there was a paper released that analyzed the masking in BERT in more detail and found that a higher mask percentage is actually even better. So you can even mask up to 40% of the tokens and have a better performing model, which is pretty interesting. So you can imagine with 40% of the tokens you're masked, you're losing out on lots of important context. All right, yeah.
We can imagine like if I'm asking a part or I'm asking a conjunction of equation with testing. Suppose in that case, if I'm asking like that it's going to open mask and something, it could be easily moved, it could be a
Sure.
So how is it going to work in the tower? What do we know in order to predict the
Yeah, so if I mask important words like that are conveying a lot of the meaning in the sentence, the model won't have a good idea of what to predict, right? Is that what you're asking?
Yeah, but the case will be same or different in that case. Suppose I'm saying with the masking some only verb only. Suppose.
Oh, only verbs?
Yes.
Yeah. So there have been follow-up papers that try and have more intelligent masking schemes where maybe you only mask the verbs or even mask the names of people or dates. These are, very meaningful things that can force the model to learn a lot of factual knowledge, right? So yeah, the people have tried that and find that for some tasks it's better to do like entity-specific masking, but in general, people just use a random masking strategy as it seems to be generally pretty good.
Could you adjust the masking rate as it trains and start with easy examples and then as it learns, mask more.
Yeah, so the question is, can you dynamically change the masking percentage during the training process? I think that's a good idea. I don't know if it's been tried before. Maybe probably everyone has tried everything at this point, but it could be interesting. I'm not sure what the effects are, but in all the models that are currently popular, they're just trained with a fixed mask percentage. So if those ideas have been tried, they haven't caught on. Yeah. Do you what? Oh. So the question is, while training this mask language model, do you only adjust the parameters associated with the mask token? So note that this model has a lot of parameters, right? Every transformer block has parameters. All of the word embeddings are parameters of the model, not just the mask embedding. All of the parameters are being adjusted with remember that if I'm drawing the backprop, right, the gradient will flow from the softmax layer into these self-attention connections, which are unmasked. So then the gradient eventually flows into all of the inputs because I'm doing unmasked self-attention, and residual connections, right? There's connections between this position and every other position in the network. So it's not that you're updating just one position here, you're updating every position. Yeah. The question is about this new paper that trained this model with a higher masking rate. Did they have to use more data? I actually don't know. I didn't read it that closely. I'll put a link to it on the website so you can check it out. Yeah. The question is, are you masking the position embeddings as well? No, you're not. Especially if you have multiple multiple mask tokens, you need the position embeddings to differentiate between them. So the position embeddings are added to the mask embedding. Yeah. All right. So and just to complete the loop between this and the two RNNs. Here, at every position of the network, like each of these final layer representations, they are fully contextualized. They're aware of both the previous words and the future words because we're using unmasked self-attention. So we have one model that is doing everything. It's computing both the information from the prefix and the information from the subsequent words and combining them into a single representation. The way that we can do this is A, using the unmasked self-attention, and B, using this masked language modeling objective, which forces the model to use both preceding and subsequent context to make these predictions. So hopefully that's clear. The training for this is, of course, done using, the softmax here is using the cross entropy loss, right? Just like we saw in language modeling, everything is the same. I mean, it's called masked language modeling. The only thing that changes is where you're applying the softmax and the fact that you have access to the entire sequence, not just the prefix. right, let me check on YouTube. Could give me a pointer on bi-LSTM versus back RNN of Elmo. Sure, I think there are some slides that I can post that explain this. The pre-training supervision signals are less for BERT because of the masked language model. Yes, that is correct. And if we go back to the, if we go back to here, it becomes clear why, becomes clear why that is, right? Because here in language modeling, normal left to right language modeling, I would get an error signal at every position in this time step for predicting the next word. Here I'm only getting an error signal for one of the 4 positions, the one that was masked. So I have 1/4 the training signal in any given, 15% of the training signal for BERT compared to the language modeling case. And they have some nice plots in the BERT paper that show that this is actually, less efficient than the language modeling in terms of number of training steps required, but it also has its own advantages that we've talked about. Okay, so now let's move on to how we actually use BERT to solve a downstream task. Yeah.
So you talk about the loop. When we consider the loop concept, we consider where has been back.
Yes. So when you're computing the loss, the cross entropy loss, it's only at the time, the positions that are associated with a mask token that you compute the loss. Yeah, so every input you randomly select some positions to mask, 15% of the positions. So if I saw this training example again in training, I see it many times, right? Sometimes I might mask students, sometimes I might mask students and books, you know, every time I'll mask randomly a different subset. Yes. Okay. Yes. Yes. So the question is, when training, do we see this training example many times? Yeah. So I mean, it does depend on the size of your training set, but in general, you'll do multiple passes through your training data, and you might see this sentence multiple times and mask different words each time. So the question is, if you wouldn't the model memorize what exactly? I mean, you're training this model on a huge number of sentences, so it's first of all not going to memorize all the sentences. What if it sees many different inputs that begin with students open there, right? Then what can it do? So yeah, I mean, in general, it will memorize some things, but it'll also be able to generalize to new constructions. Okay, last question. Okay, that's a good segue into the next part. How do we evaluate how well our model did? In the mass language modeling part, you can measure the loss, right? Like, how good is the model doing at predicting the masked out word? The cross entropy loss, right? So you can't really compute perplexity here because you know, you're not computing the probability of the sentence. But you can compute the cross entropy loss and then see if it's going down or where it's flattening, and then stop training then. Okay, but no one, as I said, actually is using these math language models for that specific task, right? It's rare that you care about having all of the text you want and you just want to fill in one missing word, although it could be useful for like spelling correction or typo fixing or something like that. You really want to use this model to solve other tasks that you care about. So given BERT, and remember in Elmo we had our pre-training task and then we had our downstream sentiment neural network. Here it's going to be slightly different. So our pre-training task, so how do we use BERT to solve an NLP task like sentiment? So we've already talked about this pre-training task, right? Like students mask their books. We pass this into what we will call BERT. So BERT is just a bunch of layers of unmasked self-attention transformer blocks. And we're going to get a bunch of vectors. And whoops, that's too many vectors. And we're going to predict open. So we're going to call this the pre-training task. And now we are going to transfer this model, which means after we train this BERT on masked language modeling, we take its parameters and basically we copy them over to initialize a sentiment model. So here I might have a sentence, this movie is good. And I'm going to take my same BERT model, which has now been pre-trained, and I'm going to make it predict positive. So these two models here, and so we're going to call this our fine-tuning task. Here, as an example, we're using sentiment analysis. So the fine-tuning task is also called a downstream task. This is the one we actually care to solve, right? We might be a company and we want to build a sentiment classifier because we're getting a lot of reviews about our products and we want to know how our users feel, right? Our pre-training task is not really one that we care about. Like masked language modeling, it doesn't have any immediate use case. Its use in this scenario is strictly to learn a lot of interesting, useful properties about language, which can then be leveraged to solve the downstream task. So what does this actually mean? What does fine-tune mean? So let's take a look at the second phase here, when we already have pre-trained our BERT model to solve masked language modeling. How do we now get it to solve sentiment analysis? So in Elmo, what we did was we took the hidden states, like these ones up here, and we put them as input to a different neural network to solve the sentiment analysis task. And that sentiment neural network was trained from scratch. In BERT, we're going to do something different. We're going to use the exact same model that was pre-trained to solve the sentiment task. We're going to add only as minimal new parameters as we can, and we're going to leverage the pre-training model for almost all of the computation. So let's take a look at how we do this for text classification tasks. So the first thing to note is that BERT appends a special token at the beginning of every input sequence. So I haven't shown this above because it would have been too confusing, but now that we have learned about the masked language modeling objective, every single input in BERT begins with a special token called CLS, which stands for classifier. So this is where, if you're using BERT in a downstream task and your task involves classification, you probably want to place a softmax layer over this classification token, CLS. So it could be something like this movie is good. Wow, that was really bad, huh? This movie is good. So this is an example that I get in my sentiment data set, and I prepended the CLS token, which is a special token. Now I pass this whole thing into BERT, and I will get a vector associated with every single token in the input, including one for the CLS token. So this is a special token used for classification tasks in the fine-tuning process. So I put the sentence through my pre-trained BERT model. I get these representations, and now I will put a softmax layer over the CLS token to predict positive. So compare it to Elmo. Here, I don't have a separate sentiment neural network, right? All I'm doing is using my pre-trained BERT model to get these representations, and then I just put a single softmax layer on top of the CLS token to solve the task. So this part of the network, the softmax layer, is trained from scratch on the labeled sentiment data that you get. So this is trained from scratch. This part of the network, BERT's parameters are fine-tuned via the sentiment signal. So in Elmo, these parameters were frozen, right? The language model was not changed by the downstream task objective. In BERT, the downstream task actually does affect all of the parameters of the transformer masked language model. So if we're looking at the backprop here, we're doing this fine-tuning process. We get an error signal from our softmax layer. We backprop through the CLS token, which, remember, is doing unmasked self-attention. So this error signal will propagate to all of the positions. It will affect all of the layers in BERT and eventually go all the way down and change all of the word embeddings as well. So in Elmo, up here, we said that the fine-tuning process, we didn't actually have one, right? Because the error signal stopped at the sentiment neural network and did not propagate into the language model. And we said that was because of reasons of efficiency. But in this case, we are going to propagate down all the way into the entire BERT model. So one reason for this, in addition to it just being better to specialize the BERT model to the downstream task, is that here we've added very, very few task-specific parameters. The only thing we've added on top of our pre-trained BERT model that's new here is the softmax layer, which predicts positive or negative, right? So because we don't have a separate neural network on top here, we just have a softmax layer, it might even be better to fine-tune the BERT model, so because we're using it for basically like 99% of the computation here. So that's just the general idea. In the BERT paper, they talk about having a special pre-training objective on top of the CLS token called next sentence prediction. You might have seen this if you read the paper. There were follow-up papers, including the model Roberta, which is an improvement over BERT, that showed that objective is not necessary for making this work, so we're not going to discuss it here. But yeah, basically this is the approach that you take to solve any text classification task with BERT. So compare this to the approach from pre-2018, where you get just text of reviews, and you have a model that's initialized randomly. It's trained from scratch on just millions of sentences from reviews. This model, the BERT model is trained first on a huge amount of unlabeled data, so it learns a lot of information from that. And then we just add a small softmax layer on top to specialize it to any arbitrary text classification task. So we really have taken a lot of advantage of this transfer learning paradigm to transfer the knowledge from the mask language modeling task into a model that can actually do sentiment analysis. That is the overall idea. Okay, any questions? Yeah.
One way of trying to predict the missing order. So when you add the softmax layer, are you replacing BERT's original kind of classification layer?
Yeah, that's a great question. So remember up here, I had this softmax layer that predicts the identity of the mask token, right? So the dimensionality of this representation here is the size of the vocabulary, just like in normal language modeling, right? It has to predict which one of the word types in my whole vocabulary fits into the mask token. In sentiment analysis, I have two classes usually, it's positive or negative, and so I don't need like that enormous softmax layer. So I basically throw away that softmax layer, the one that was used in pre-training, and replace it with a randomly initialized one that only projects the representation into 2 dimensions, so that I can then use it for a sentiment. Other questions? Yes. Sorry, can you say that again? You mean at the pre-training phase? Or? Oh, yeah, I'm not actually sure what your question is. Oh, yeah. So the question is, can we use the same setup to solve multiple downstream tasks with the CLS token? Yeah, so the same setup if I wanted to do like, I don't know, topic classification of a document or something, I would still just put a different softmax layer on top of the CLS token and fine tune it with the downstream task signal. You can also combine different tasks together, and so you can, for example, pre-train your BERT model. You can fine tune it on sentiment analysis, and then you can fine tune it again on something like topic classification. Sometimes if you have tasks that are similar to each other, you can get better performance. I'm not sure if that is what your question was about, but I see some in YouTube. Elmo could be used for fine-tuning as well. That is true. We could have fine-tuned Elmo, but it was computationally very expensive. Fine-tuning is not, I mean, in as much as a transformer is easier to train than an RNN or LSTM model, it's more efficient, but nothing else makes it more specialized. The separate neural network on Elmo could also be simple as a small softmax. That is true, but you need a way to do the composition of the hidden states. Yeah, in general, we added a full separate neural network, like an RNN on top. Are we getting non-contextualized embeddings for words in the softmax layer? Can we treat them like that? Yes, so in the softmax layer, the dimensionality is like the size of the vocabulary, sorry, the hidden state dimensionality by the size of the vocabulary, so you can look at each row in that matrix as if it's a, or each column, I guess, as a separate word embedding. Normally, you can tie the word embeddings to the softmax embeddings, which means you use the same matrix in the input as well as the output when you're doing mass language modeling or next word prediction. Okay, so I guess we have 3 minutes left, so maybe I will just finish by going over the terminology that I've been using today, just to clarify it, and then we can continue with how to use BERT for different types of tasks tomorrow. So again, remember that we do have class tomorrow as well. So pre-train, I said that a lot this lecture. What does it mean? So start with a randomly initialized model and train it with a self-supervised objective. So far, we've seen 2 self-supervised objectives: next word prediction, like language modeling, and now masked language modeling. In both cases, we can get the labels for free, right? So these could be LM, masked LM, and the data is free, which allows us to train really big models on really huge data sets, right? Big models on big data. Another term we used is freeze, which refers to the fact that we do not backprop into the params of the pre-trained model. Using the downstream task objective. So in Elmo, we froze our pre-trained language model and we trained a separate network on top. Finally, the last bit of terminology we used was fine-tuning. And we'll hear this a lot more in the semester, which is when we backprop into the pre-trained model using the task-specific signal. So in general, keeping a lot of the model parameters frozen is more efficient. You can train faster because you're not computing all the gradients deep into the pre-trained model. On the other hand, fine-tuning appears to work better for most tasks because you can specialize the entire model to solve the downstream task. So there's a trade-off. In Elmo, we froze the language model. In BERT, we fine-tune the language model. And in both cases, we are using a pre-trained model as the first step, and then we are transferring the model to solve a downstream task. All right, any final questions?
Earlier you mentioned that language models can be applied to targeting. That's kind of interesting.
Yeah, I can post that paper on the website. There's also the paper about 40% masking that I'll post as well. Yeah, that is pretty crazy. Yeah. Is fine-tuning the same as downstream? So downstream is the task that you actually care about solving. It's not the pre-training task. Fine-tuning is only accomplished on the downstream task. So like if I have sentiment analysis as my downstream task, I will fine-tune my model on labeled reviews from that. Yeah. Yeah. Yes, so when I'm doing fine-tuning, the softmax is trained from scratch. That's so the softmax layer is getting trained, it's randomly initialized, and it's trained using the signal from the downstream task itself. So like the labeled reviews in sentiment analysis, how the model is doing at predicting positive or negative, that signal would be used to train the softmax layer, and it would be used to fine-tune the already pre-trained parameters of the big language model underneath that. Yeah. So the question is the output deterministic? If I pass the same input with the mask into my model, will it predict the same distribution every time? Yeah, I mean, there are some non-deterministic things in the model like dropout, which are usually turned off at test time, so everything is deterministic. You'll get the same predicted probability distribution for this mask token every time you feed in the sentence. Oh, so the question is if we wanted to actually predict the token that goes in the mask. So remember that, first of all, we don't really care about this task, right? So we never need to actually sample a token or generate a token in the mask token. The sole point of this task is as a pre-training task so that we can use it to solve downstream tasks. But if you wanted to predict a token, you could sample from the distribution, or you could take the argmax. There are more complicated decoding methods that we'll talk about later in this semester also. Yeah, last question. So the model is always trained using the ground truth word that occurred in the document as the target. So if closed occurred in this context, it's always trained to predict closed. In some other context, maybe opened occurred that are similar to this one. So eventually the model may learn, to put some probability mass on both opened and closed. That's probably what would happen. All right, so that's it for today. We will continue with how to use BERT and some variants of BERT tomorrow.